Chapter 1, The Science of Physics. So physics is the study of the interactions of matter and energy. So what we're going to do today is we're going to do two things. We're first going to look at graphing, and then we're going to look at percent error. So why do we bother doing a graph? Well, the whole purpose of a graph is this is a visual way that we can easily see what's going on in a particular situation. So even though there's all different types of graphs that we're going to be using, graphs are easier to read than tables, but a lot of time we can look at the shape of a graph, and the shape of the graph can give us information as to, as far as physics is concerned, the motion of an object. So let me show you what I mean. In physics, we're going to graph certain physical quantities, and there's different types of graphs. We have a position versus time graph, and we know that on a position versus time graph, the slope of the line is the velocity. Well, just by looking at the shape of the slope of the graph, I can tell what's happening to the motion of the object. So if I have a horizontal straight line, a horizontal straight line represents a zero slope, so this would mean I have a zero velocity. If I had a straight line like this represents a constant slope, because if I took the slope of any 2 points on that line, it's going to be the same thing. So this tells me that I have a constant velocity. And then if I had a position versus time graph like this, that is a curve that's changing. So I see that the velocity is changing. So the changing velocity means that it's actually accelerating. And then whether I wanted to know if it was increasing or decreasing speed, we could look at, I like to draw little pretend tangent lines, and I see that the slope is increasing, so then I know that it is accelerating, and it's a positive acceleration. So going back to the notes, we see that graphs, again, they're easier to read, and this is why we're going to be doing graphs. When we do labs, we also sometimes have error in our measurement. So the error of a measurement is the amount by which the measurement differs from a known accepted value. And so we're going to use percent error. So when we do a lab, sometimes we're going to calculate a value, but if we already know the accepted value, we can find that difference, and that difference is called percent error. Now we're going to be doing this on several of our labs throughout the year. So this is an equation that you need to have memorized. And we will have this on our first test as well. So percent error is the accepted value minus the measured value. This is what we obtain in the lab, divided by the accepted value. Now when we do this calculation, it comes out to be a decimal. So if we want it in form of a percent, we multiply it times 100. So here's an example. It says, suppose the measured value of the acceleration due to gravity is found to be 9.44 meters per second squared. Now the accepted value is 9.8 meters per second squared. So the difference is 0.36. So if we just put this in our equation, so again, what we need to do is we need to identify and say this is the accepted and that this is the measured value. So then when we put it in our equation, and it's going to be the accepted minus the measured divided by the accepted and then multiplied times 100, that gives us our answer in the form of a percent. Okay, now we're going to look at our handout on graphing because there was hardly any notes here. So there's a lot of specific stuff that we need to know for this class. So frequently an investigation will involve finding out how changing one quantity affects the value of another. The quantity that is deliberately varied is called the independent variable. So if I want to measure something and I decide I'm going to measure it for every 1 second, I'm deciding before I even do the lab, okay, every second, every 1, 2, 3, 4, 5, I'm going to then measure something else. How far did an object go every second? So the quantity that changes due to the variation of the independent is called the dependent variable, because this is dependent on that. More often than not, the relationship between the independent and dependent variable is not obvious simply by looking at it in written data. However, if one quantity is plotted against the other, the resulting graph gives us evidence of what sort of relationship, if any, so we can see if something's a direct, indirect, exponential, exists between the two variables. So when plotting a graph, these are the steps that we're going to take. Number 1, we're going to identify the independent and dependent variable. Number 2, choose your scale carefully. So what that means is when you're actually drawing a graph, you're not going to draw all your little numbers like 1, 2, 3, 4, 5, and then up here to some, and then have this minute little graph. Actually, what you want to do is you want to try and use all the graph paper and spread it out as much as possible. Now remember, when you do that, because this gives you more of a true shape of the graph, so if we go back here to number 2, it says choose your scale carefully, make your graph as large as possible by spreading out the data on each axis. Let each space stand for a convenient amount. Choosing 3 spaces equal to 10 is not convenient because each space is an awkward fraction. Choosing 5 spaces to equal 10 would be better. To avoid a cluttered appearance, you do not need numbers in every space. So if we look down here at the sample, we see that every 5 boxes is 1, because how do you know how you're going to spread this out? What you do is you look at your table. And I said, well, this goes from 0 to 5, so they decided to use every 5 as 1. This varied from 0 to 7.5, so they used every 1, 2, 3, 4, 5 to equal 0.3. Now, do these have to be the same? No, they do not have to be the same. Plot the independent variable on the horizontal axis. So you always know that the independent, the one I decide ahead of time, is going to go horizontal. So I decided I'm going to measure the force every Newton, so that's going to be here on the horizontal axis, and then I'm going to measure the elongation. This is obviously a lab having to do with Hooke's law, and the elongation, that means how much a spring stretches, and it's measured in centimeters. And the dependent variable on the vertical axis, so you need to know the dependent is going to be vertical. Plot each point with a dark dot with a circle around it. Label each axis with the name of the variable and the unit. So here I am measuring the force, and the unit is newtons. Here I'm measuring the elongation, and the unit is centimeters. Title your graph. Then it says, using a ruler, darken the lines representing the axis. Title your graph. The title should clearly state the purpose of the graph and include the independent and dependent variables. If the data points appear to lie roughly in a straight line, draw a best fit straight line. Now, it's not necessarily going to be a straight line. If it was a curve, you would do a best fit curve. Have as many points as possible. So if we look at this data here, and I'm just looking for a ruler, you notice we never ever in physics play the game called connect the dots. So we don't want to do something jagged. What we do is we do a line that best fits all those points. The mistake sometimes that people make is they have data like this, and they kind of do this. And we don't do that. Never connect the dots. If the points do not form a straight line, draw the best smooth curve as possible. All graphs do not go through the origin, 0, 0. Think about your experiment and decide if the data would logically include a point 00. For example, if a cart is at rest when you start the timer, then your graph of speed versus time would go through the origin. If the cart is already in motion when you start your timer, your graph will not go through the origin. So here it says below is a graph using good graphing techniques. Go back and check each of the items mentioned. So now when we flip over, it talks about interpreting graphs. In laboratory investigations, you generally control one variable and measure the effect it has on the other variable while you hold all the other factors constant. For example, you might vary the force on a cart. So this just shows variation. So if this varies with that, this is what's called a direct variation. We see that this is a curve. So here, when we look at this, there are three relationships that occur frequently in physical processes. If the dependent variable varies directly with the independent variable, the graph will be a straight line passing through the origin. So that's this figure, figure 1a. If y varies inversely with x, the graph will be a hyperbola. So here's my hyperbola. And the third relationship is one in which y varies directly with the square of x, and this gives us a parabola. So those are the three types of graphs. Sometimes you need information about a value that you have not determined experimentally. Reading from the graph between the data points is called interpolation. So this is an extremely important word. So reading between the data points is interpolation, and reading beyond the data points is called extrapolation. So those are two important definitions that you need to know. And then this goes on and talks about propagation of error. So again, here are the different types of graphs that we'll be dealing with. And this is why it's easy, because you can look at this graph and see that this is a direct variation. So as one varies, the other one varies. This one we see is inversely. And then we see that this one is with the square. So you can tell this, instead of looking at numbers, which would be difficult to look at, you can just look at the shape of the graph without numbers and tell. When we get to chapter 2 in this class and we do motion, we're going to look at graphs and we're going to interpret the motion without any numbers. They're going to look like this. And that's it.